Hello, welcome. My name is Livranka, and today I'm gonna be showing you what I've been up to. So, the last few videos I did them in Spanish, which is my native tongue, let's say. But since those have been getting next to no views, I figured, well, I'll just do everything in English back again and forget that I actually speak Spanish in my day-to-day life. So anyhow, I'm going to today show you the Peso programming language. This is a language which I designed, that I'm still designing, and for now it is entirely interpreted. Our plan is to eventually make it compiled. I'm still getting how do you say, learning the ropes of assembly, so that will take, I don't know, a couple more months, give or take. But anyhow, rather than demonstrate an already created a file, I'm going to make one from scratch. All right. So if I go to my console here, all right. So I'm going to clear this tasty log here and make sure that I'm on my folder. I'm going to use this with this function here. Okay. So let's make a new file. Okay. Let's try. I'm going to utilize another function here to make a couple calls to Notepad. And let's call this one, why not, example.p. Alright, and yes, I want to create a new file, and let's show you the editor here, and we have a blank file. So how do we start? Well, the first thing, we have to draw 16 money signs. Alright, that's this byte value over here, and I also have to set, alright, there. Alright, yes, so I have syntax highlighting, which is convenient. So why do we have to do this little signature here? This has to be at the start of every file. The first 16 bytes need to be this signature. Why is that? And rather than explaining, I'm going to show you. Well, I'm also going to explain, but I'm also going to show you. I'm going to do both things, okay? So let's see. I need to grab, that's Grim Kerr. What was the name? No, wait, that's kernel. And I think it was mem, and that's kerbin.c, no? Yep. Yeah, there we go. Let's change here to editor. Good. Alright. So here's the file, which does most of the I/O and things. And the way it works is it checks for a signature. Alright? It checks for a signature on a 16-byte, no, 16, yeah, 16-byte signature on every file. And this is part of my framework that I've been working on for the last year. And the idea for this is to sort of it's like a unified developing environment. I'm hesitant to call it an IDE, right? Because the idea is you choose whichever C compiler you want, and you choose whichever editor you want, and you just have some background code gluing things together. But yeah, the main idea here, because I have different binary file formats, is that we utilize this, which one is it? Make bin, which opens a No, this doesn't open. No, this simply this is just initialization. Forgive me. No, the function is here, rdbin, right? So what this does simply, it opens a file, right? But we want to check that it's a valid file, and there are many ways to go about that. And the quickest way is to simply check for a signature. And of course, one could simply fake that signature. That's, you know, simply a thing that happens. And if you do that, and the and the system attempts to read that file with a falsified signature, let's say that you put the signature for an image file on what's actually a text file, yeah, that's not going to work. That's a seg fault, right? That's a hard seg fault, and there's no way around that. But I think that allowing for that kind of user error, which has likely no possibility for malicious use, and you know, if it had, it's a developing environment, not a it's not like something you would deliver. It's not a production code. It's internal stuff. So, you know, on the security basis, I'm not concerned. It is simply an oddity of the system. Okay, we good? Now you understand why we have to do these things that we do. Okay, so back to Peso, alright? How do we declare variables? That's a question, I figured. I wasn't sure how to do it in the most natural way, and the way I solved it, it's not the most natural way. What we do is simply we have context. We have different context, and for variables we utilize reg, right? So reg, you give it a name, and let's say this is going to be, I'm not feeling very creative, so it's simply going to be vars, alright? So vars, and every statement, and this is true for every statement, we terminate, except for the signature, which is not a statement, we terminate it with a semicolon. And yeah, you know, you could terminate it with a semicolon, it's meaningless, but alright. So white space and semicolons are quote-unquote meaningless. If you have two semicolons back to back, that's nothing, that's going to do nothing. If you have a semicolon, some white space, and another semicolon, that's also going to do nothing. Okay? New lines also do nothing. The only thing that counts is keyword, and after a keyword you have a certain list of arguments. So reg is a keyword, it takes one argument, and that's name. Alright? This is the basis of how everything works in this language. Keyword, arguments, that's that. Alright? And so we don't really need to add anything besides the semicolon in order to separate our statements. So we could simply here declare a variable right here, and we're going to create a char. And I'm going to go more in depth on how the allocation is managed in a second. But first, let's do something with char. All right. So here we can initialize it. We can give it a value over there. You can put the equal sign if you want. It's not necessary. It's not strictly required. I personally do not like it. Char, like I have stated, is another keyword. It takes at least one argument, and that would be name, and then a variable size, a variable number of arguments, and that would be values to fill that variable with. And what's interesting about variables in Peso is that all of them are aligned to a 16-byte boundary. That would mean their addresses are always divisible by 16, so they always end with a 0 in hexadecimal, right? So it'll be, 1020 all the way to F0. And what this means is that basically when you ask for a single character, it's going to give you a buffer with at least 16 bytes. With at least 16 bytes. That's guaranteed. Why? Why do that? Well, I'll get to that in a minute. This is going to be the pattern. There's many things to explain, and I want to sort of hurry along here, show you a little bit what this is about. So I'm going to de-initialize that variable over there, and now we're going to give the program some instructions, alright? And we do that with the keyword proc. And proc is a context keyword, and just like reg, you can tell by the lovely purple pinkish color, right? And so the way proc works, same as reg, it's keyword name, nothing more, right? So let's call this main. You can call it anything, you can call reg anything, well, most anything except reserved words, of course. And let's just do a simple operation. Let's assign a value to x. We can do that with the copy keyword, and let's copy into x the value of money. All right, let's copy money to x, and we want to exit with x. All right, and so if this is at least for now, this would mean just return that. It's like an exit code, right? Now we need to tell the interpreter where the entry point is, and that is something you can simply do with another keyword, that's entry. Simple enough. And fun fact, you do not have to forward declare. This is a multipass interpreter. How about that? Have you ever heard of anything like that? And yes, very much, we do not have to separate these things. Like I said, we can do this entirely in one line, and this should still work. Now I'm not going to do that because it does not look very good. Alright, so let's tidy this up a little bit. Okay, so this is a very basic program that doesn't really do much, but it's good enough for a simple demonstration, a hello world of sorts, and we'll get to an actual hello world in just a second. Like I've been saying for the last 12 minutes, about to be 13 minutes. So let's bring out the console here, and I'm going to try and interpret this for you. So we have to save this file, so let me do that. Oh, it's created. Nice. Alright, so let's see if we can call the interpreter on this. So I'm going to use another function, that's lie_run, and the interpreter name is mam. You can find the source code for mam in my repository. I will link to it in the description, do not worry. And we need to provide mam with the through the f flag with the file name, right? And this I called example.p, if I remember correctly. So let's try that, and there we go. All right. And so, what do we get here? Well, first and foremost, this is from the Cur framework, like I touched on briefly at the beginning of the video. I've been working on a framework of sorts, or what did I call it? A unified developing environment. It doesn't matter. It's a framework, all right? It's a bunch of libs, and you can use them to do stuff, all right? And one of those things it provides is the mem struct, which is simply a way to manage your memory. And it's useful because it logs every allocation and deallocation. So that's a handy way to know. It's a sort of debugging utility, you can know if the call to free was made. And more importantly, you can tell if everything you allocated was read at the end of execution. So, handy thing to have. And you also get the names of the things you've allocated and their size. That's nice. All right. So, moving on to our code, here we can see the program we input into the interpreter. And here we get our output, and that is simply code 0x70. That's actually 70 because it's hexadecimal. What does that mean? Well, we can take a closer look at that if we repeat our previous command, but we also pass the ML flag. That stands for memory layout, and you're about to see what it's like. It's really cool. Look at this. So every context keyword in Peso corresponds to a data structure, and every data structure is registered into this memory layout, right? And so you get here the name of the block, right? That's bars, and you get an address. And whenever you utilize the name bars, you're referencing this address right here. And so you can utilize these names as a shorthand to reference these addresses. And so you can utilize this for jumps, and we're going to get to jumps in a minute, like I've been saying for so many other things. Let's look inside vars, and we have x, our x here. And if you look closely at x, you can see that it terminates, it ends, or no, this is Little Indians or big, and well, it actually begins. It actually begins. So this is the least significant byte. It actually begins on 70. And what do we get here? 70, we returned x, and so it is actually returning the address of the variable. Isn't that nice? But what if we want to print out the ASCII representation, or rather I would say the text representation of that character, right? Because we want to do strings. We like strings, don't we? So we can do that, and let's check here, and for that we can utilize another keyword, and that's web. So I don't know how I came up with that name. I don't remember exactly, but I like the way it sounds, and I'm used to using it, so it just stuck. And the use of web is it simply tells the interpreter what's the typing mode we're using, right? And so we can utilize to say, char. We're dealing with chars. Every command after this interpret it as a char operation, right? And so instead of having multiple operation names, so for instance, char copy, for instance, you just have copy, and that's that, right? And so you just change the mode of the call, let's say, right? You change the typing mode whenever you want to. We can also do what's the name, wide, when we want to deal with 2 byte. We have word, and yes, I know that word, it's usually 16-bit word. No, this is a 32-bit word, okay? We clear on that? 32-bit word, and long for 64-bit, all right? And we also have string, which is a variable size of characters, okay? Well, it could be wide characters as well. It could be words, it could be longs, any type that you want. But generally, characters, at least in without an Asian locale, or Arabic, I guess. I should know better about that. But generally with just characters, you're good enough. So okay, let's try printing this out with web set to string, which will actually change the return mode of this procedure, of this function, so to call it, this ugless function. So okay, let's move to our console. All right, and let us repeat the call. And oh, that's not good. That's not good at all, my friend. That is a sec fault. All right, I was not expecting that. Let me debug it for a second. All right. Let's see here. Where did I go wrong? Oh, right. I think I need to initialize this, don't I? Well, worst that can happen. Let's just give it some value something, alright? And yeah, that should work, I believe. Oh no, wait. I think I know. Let's try this. Let's try it like that. Weird, it should work with number representation, but you know, I'm getting confused perhaps. Alright, so let's try that again. And there we go. It exits with code money. And of course, we're not limited to a single char because, like I said, it is I can't find my there. Like I said, this is a multi-char kind of typing, so we can, you know, input a string, and we can do about 16 bytes of string, because that's what a char guarantees us, 16 bytes. So let's try that. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do I know how to count? That would be my question. Let's just copy this over and let's just write it out. String and a bunch of money. Loads of money. Alright, let's try that again. And there we get string and a bunch of money. Okay, let's take a look at the memory layout, because that's always fun to do. And as you can see, we have also a line in a memory layout for every instruction. As you can see here, I'm going to show it line by line because this is actually fairly interesting, I believe. So first line, that's wed string. So let's look at it. It begins here. And you can see this thing is from how do you say, right to left. So this would be the least significant byte of the first 8 bytes, and this would be the second half, and here is the least significant one. So this would be byte 0, and this is byte 16. Okay, all right, good. So let's see if I remember correctly. This is my this is my own structure, bear in mind. So if I don't remember it, that's a problem. But the first half word, 32-bit word, need I remind you, this would be the location of the instruction itself. So every instruction, every keyword is located within a table, an internal table. And so it utilizes this index to look up the correct instruction to call. Then this would be the size of the instruction measured in what we call memory units, mem units, and that's simply put a 64-bit long. Okay, what I like to call a line sometimes, and some other times I refer to this entire thing as a line, but more often than not, a single 16-byte block, that would be 2 memory units. Okay, so moving on. The next unit, the next memory unit would be a sort of a magic number for interpreting the token for the instruction. Every instruction possesses a number of tokens which break down the arguments. And so we have this crafty one, suicide. That's no, it's not actual suicide, just the name of the band. And over here, this would be for operators. This is utilized when you're doing a math or logic within an instruction. In this case, it's not utilized. And here we have a value, right? A single numerical value, or it could be a string too, or some other kind of array. And then next up, we have another magic number, which is free block, as you can see. Imagine the 9 is an R, and you can see free block. So this simply tells us that the block is uninitialized, so it has not been tampered with. That's all it says. All right, so moving on next instruction, that's copy, and I'm going to speed up through this so you know what this means. This is the magic number to represent the following token. Here we have operators are empty, and we have a value, and the value is an address that's of X, and we can confirm that it is the right address, as you can see. So okay, can we write to this memory location? Yes, we can. Yes, we can, at least on interpreted, at least when running on the interpreted mode, we can write to this memory at runtime. So it's sort of a meta-programming funky kind of thing, which is interesting in its own right. Then we have the next token, and it starts with the magic number separate. Imagine that this is an SE separate, so that indicates a comma. The way that the interpreter is looking at the instruction, it would just read every token until it comes into a separate token, which basically says, that's one argument, evaluate that, and whenever you're called again, we read the rest of the instruction. Okay, so no operators, of course, because it's an empty token, right? Which could be used as spare memory, though that's not recommended. But if you wanted to, you could do it. Then next up, we have char star. That's a little bit more. That's a little bit harder to read, but imagine this is an STRR, right? And there's no good way to make an H, so I just use a 4. Well, char star, right? And that's the first half of the unit. The other half is the length of the string, because we do not measure strings by way of null termination, though we have null termination. I'll get to that later on. We simply record the length of the string, and as we modify the string, we modify its length. Simple enough. And because we've written it down as a constant, that constant string is saved as part of the operation. And look how we do not have a free block at the end of this, because it needs more memory. The instruction needs that extra unit of memory to allocate the string, and so it utilizes that additional space that it has. Like I said, you can utilize these empty unused blocks as spare memory. Unless you know what you're doing, it is not a good idea, because things can get a little bit weird. But if you do your math right, yeah, you absolutely can. Then the final instruction, we just have 7, so that would be, what is it, exit? Boy, I don't remember. Well, it doesn't matter. I think it is exit. And, well, size, you know what this means. Fetch boy, that means, yeah, that's fetch boy. That means grab this pointer or something along those lines, and we can see it's given an address, and that's X, and we can verify that it is indeed the right address, as you can see here. All right. So that was quite a journey. That was quite a journey just for 3 instructions, but you know, that's low level for you. And this is, in real talk. This is all written in C, so technically it is still high level programming. You know, I hate to break it to you, man. This is not real low level. You've never seen real low level, right? So okay, let's try allocating a little bit more space for our strings, right? Because just 16 bytes, that's too little, right? That's too little space, man. We need more space. We want more space, don't we? Okay, so let's try that. And what I want to do, if I minimize here, oops. Okay, here. So if I'm going to explain why I delay so much between transitions is because I have only one monitor. So yeah, sucks to be me. So anyway, when we need more lines to work with, right? We need more lines. So a 16 byte block for our values. What we can do is, well, because convenience, when you're declaring a string, if you initialize it as a string and you just put a bunch of values here, and what I'm going to do, I'm just going to return this as it is, and I'm going to pass it like this, and we get our return right. And as you can see over here, we get a whole lot of additional space that's at least long enough to hold our string, right? The string we initialize that variable with. But it also has this weird, funky, kind of cool property in which the number of lines allocated for that name, for that block, will always be a power of 2 that's divisible by 16. So that's another cool thing. So the number of bytes, the number of total bytes of a block is always divisible by 16. And why do I do that? So that every single block, and I promised I would get to this, every single block that's addressable by name is 16 aligned. And you know, you might think, well, you know, that's cool and kind of crazy, but why? And you know, it simplifies a lot of operations. When you, for instance, when you need to validate a pointer, you need to know if it's a valid pointer. Well, first and foremost, it has to be 16 aligned. No way around it. Every single pointer is 16 aligned. No way around that. Or at least every pointer that has a name at how do you say, at compiler interpreting time. The user can of course point to an unaligned address and write to it, but when it comes to storing metadata, for instance, length of strings, or the type is a given value was declared defined as, those kinds of things, you want to store a little bit of metadata. And so you need a quick way to correlate things between one another, and you need to do validation and things like that. And if you just align every last pointer to 16, that's, let me tell you, that simplifies the math. You ever try to do math with pointers? It's simpler. It's much simpler if you know things like this in advance, right? So anyhow, enough of that tangent. Give me a second here. So, okay, enough of that. Let's go back to strings, all right? So we get at least enough memory to hold that string we asked for. But what if we don't have an initial value and we just say, I want a big old box, and I'll fill it as I please, right? I'll fill it as I please. I'll do with it as I want, whenever I want, when I want. Well, there is a way to do that, and the way, and that way would be rather, if I get rid of the initialization there, you can say char2, for instance. And what char2 does is what was the formula? Well, what the hell, I can just show you. So let me find the file here. Alright, so that's a little bit too big. And here it is, okay. So that would be, alright, so it's a power of 2, that's 2 plus magnitude, and magnitude here would be this little number here, if I'm not mistaken. Or it could be, I believe I've misplaced my notes, but wait, let me do the math on that one real quick. So that would be 2 to the 2, that's 4, so plus 2, that should be, yeah, I definitely do not remember. Yeah, I think the minimum is 3. I believe that the minimum is 3, so that would, no, the minimum should be 4. Well, you know what? I'm not going to I'm not going to dig into my notes because we could be here all day. But the point is, char and no number gives you 16. Char and 2 gives you, how much was that? 32 bytes. 3 should give you 64. So let's actually confirm all of these, because I don't want to make a fool out of myself, not more than I need to. Alright, so let's try that. Let's say char 2, 3, and let's do 4, why not? And we'll just count the number of lines given to us. Okay, so let's clear this mess and let's call this thing again. Ooh, what's that? Look at this, my debugger at work, giving me error codes and all. That's beautiful, man. Alright, so multiple declarations of value y. So I have some checking, some quote-unquote compile time checking. It's interpret time checking right now. But yeah, useful nonetheless. So let's correct that little mistake. That should be Z. Alright. So let's try this again. And why isn't this? Okay, here we go. So let's run this again. And here we go. Okay. So x2 is giving us 2 lines, 2 16-byte lines. Char3 is giving us 1, 2, 3, 4, and char4 is giving us 1, 2, 3, 4, 5, 6, 7, 8. So it's always a power of 2. It's, maybe it should increase by a constant amount, maybe that would be useful. But doing it like this, when you have to store the size of the array, you can just store that magnitude value and then just, calculate it. Which, to be fair, maybe it's not such a good idea. I might change it. I don't think I will, but maybe if a sufficiently good argument for changing it is presented, then I could change it for something that's maybe more intuitive. Maybe increasing by a constant amount. But it's nice because with magnitude you just have to store a smaller number for the size. So you can utilize right now. I think I'm utilizing a single byte for the size of the array because it's just a power of 2. So you can go up to 2 to the 256, and that's a big old number, big old number. It's I don't want to say more stars than there are in the galaxy, but it might as well be that high of a number or higher. I'm not entirely sure. I'm a lousy mathematician. So okay, we can have big old buffers. Let us fill up these buffers with things. Let's just use a single buffer for starters. And if at one point I missed a scene transition, I am very sorry. I am not going to reshoot these. It's taking me long enough. So okay, let's do... Yeah, I think 32 is good enough. And let's fill this thing up with garbage, alright? Let's fill it up with garbage. So what I'm going to do is just type random things here. Alright, so that should be big enough. Or maybe bigger. So let's make sure that I have... Yeah, I went overboard. That's okay. No problem. So, we have a buffer big enough. Let's look at how do we null terminate this. And by null terminate, I mean to say we want to shorten this string. We want to assign a new value to this string. We want to, let's say, quote unquote, initialize it, or re-initialize it, or rewrite it, if you want. We want to rewrite this buffer, and we want to get rid of anything that's after the value we give it, right? And so we could, for instance, let's say we could iterate over the... Yeah, actually, let me show you this. All right, so I'm just going to make another char here. I'm gonna call it y, and I'm gonna give it a value of 0. And you don't have to do it in hexadecimal, right? I just like to do that. And let's iterate over this, and this might take me a while to think out, but whatever, So let's do it like this. I'm going to have a separate proc, and this is going to be end, and I'm going to have a GIF. And a GIF is jump if. You also have jump, which is the unconditional version, so always jump to a given address, right? This should be the address of a procedure, but you can give it anything. You probably shouldn't, but you can do it if you want to. So we can do Jiffy. I like to call it that. I like to call it Jiffy. We jump to main if the value at y, and remember, variable names are actually addresses. This will actually be read as the address itself, and so not very good for comparison, but if I do it like this, I can dereference it and access the value within the address, or at least the first value, at least the first byte. If I wanted to access the second, I would have to do it like this, and actually, to access bytes, I have to change the typing mode to char. So, we're learning, man, we're learning. Okay, so, the first value of y, but the first value of y, why don't we give it a name? Why don't we give it a name? We can give it a name by utilizing the lease keyword. Lease. I wanted to make it alias, but that's alias, but that's too long. That's too long. That's too long. Messes up my style. So yeah, list, and list. It needs to take a string. Don't ask me why this is a string. It has to be. it makes things simpler. So we pass it a name. Let's say counter. Why not? I'm gonna say counter. And yeah, that's too big. That's too long, but you know, just roll with it, man. Okay, I'm just gonna call it counter. Counter. Okay. So we do counter, and that would be y. We get 16 bytes. So if we need another car to do any sort of intermediate calculation, we can use y plus 2 or y plus whatever up to 15. Yeah, up to 15, and utilize that and give it another alias. For now, we're just going to do it like this, and we should be able to dereference that. Okay, and if not, it would be a seg fault, and I'll see about fixing it. Just let me check. Oh, okay. I've been recording for over an hour. Okay, that's interesting. Good. Okay, so let's focus. Focus. All right. So we want to do reference to counter and check that it's been I'm going to say 32, right? So if counter is less than 32, we want to jump back to main, and we want to increase our counter. So counter, and that's that, increase counter. And of course you could also add counter 1, or I don't know, 2 if you wanted to, but you know, that's that's just increase, that's basically counter plus plus, right? But we don't do plus plus over here. Alright, so we increase. What now? Well, we want to write to x. We want to write to x. I do not remember. I honestly, honest to God, do not remember if this was fully implemented. But I think that I should be able to utilize this inside a loop. So actually, let's do this. Let's do a proc init and put this initialization code over here. Alright, so we don't have to repeat those instructions, because if we walk back to main, we would have to execute everything below main, right? And so let's have init and make that the entry point, and when it's done processing init, it will just jump over to the next procedure. That's cool. Okay, so let's make a loop time alias, which would take a little bit more time than a static alias, but a static aliasing, but it should be good enough. So let's say string. All right. Oh man, I like, yeah, I mean, let's do string. Why not? Let's do string, and I want string to be x plus y dereferenced. Oh, actually, I'm going to use counter for this. Okay. Right. So we want to use copy on string, and we want to pass it the value of 0, so that it's a null character. It will not be printed. The character is still there, but you know, we're blanking out this thing. Couldn't we do this more effectively? Yes, we could. Yes, we could. Actually, we could go 8 bytes at a time if we changed the typing mode. Let me think about this for a second. Well, then we wouldn't need to iterate 32 times. We just have to, what's 32 over 8? I always forget. That should be 4, no? 1, 2, 3. No, that's more. That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 times. Is it? I don't think it is. I really don't think it is, but 1, 2, 3. Let's wait. Wait a minute. Let's look. That's 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Oh, it is 8. How come? How come? Alright, so never mind that. So we can iterate 8 times, and yeah, why not? Let's just do long, and so now we don't have 16 addresses of y, we only have 2, but 2 is going to be enough. And yeah, it doesn't matter that it was declared as a char, we can utilize it however we want because we've allocated 16 bytes for this thing, so we can just recast it to whatever we want without consequence. Isn't that nice? So okay, let's recast that. And yes, we're going free of consequence if you do not have anything after that char, right? If you had 4 chars over here, well, it's more than 4, but if you had 4 chars over here, so 5 chars in total, and you change the type into long, then whenever you write to this first address, you would rewrite all of these. And only the last one, which is on the second unit, would be saved. Oh no, actually all of these would be lost because these are chars. These are chars, not white chars. Well, anyhow, you will lose anything that's after it. And actually, let's demonstrate that. Let's just put a value there, just randomly put a value there. And first thing we're going to do, we're going to alias it, and we're going to copy a 0 into it, into counter. Okay, let's copy that value into counter, and that will just zero out the whole memory unit. Okay, so we're done with that. We want to copy 0 into a string and 0 it out. So this will probably work, but I think it is going to segfault. When in doubt, assume it will segfault. That those are the words I live by. So okay, let's try that. And it did not segfault. Ain't I the king of kings, my boy? Okay. So we get an address because we're in long mode, and long mode will not return a number. It will just return, well, it will return a number, a long wide number. And because we gave it x, and x is an address, well, it would just spit out the address, right? So let's see, did we succeed? And we did not. Well, that's interesting. And frankly disappointing. Quite disappointing, I might say. Oh, I think I know why. Okay, so wait up. I need to the offsets are in bytes, aren't they? Yeah. The offsets are in bytes. I need to multiply. So that would be 8, isn't it? Can I do the operation? I need to. Yeah, I think that should do. Maybe. Okay, let's just go over to our console here. Okay, and let's try that again. And that's a segfault, my boy. Oh no, that was not a segfault, that was an infinite loop. We got ourselves a winner. Oh, isn't that nice? Okay, so what went wrong? Let me think about this for a second. Bitty bitty bitty. Well, we could also just increase. We could also just increase these in steps of 8 and it would make no difference, I think. And oh right, because we're exiting here, yeah, we need to jump when less than 32. So that first and foremost, but what else? Oh, I see what happened. I think it did the multiplication first and then... No, but that would have been right. Well, I'll think about it later. I'll think about it later, man. Okay, let's try this again. Okay. Let's try that. And that is not an infinite loop. We are getting progress, but we are only clearing out the first portion. Ah, that's so disappointing. I was expecting to get over this quickly and cleanly, and looks like nope, that's not what's going to happen. Well, you know, I could always just do this, right? And make these, yeah. So apparently, I have not implemented the, how do you say, um, re what's the word I'm looking for? Redefinition of aliases, right? So that dynamically aliasing, but I was pretty sure I did. Well, anyhow, this should maybe work now. I don't know. Let's try it. And if it doesn't work, well, what can I say? So okay, at least okay, we did one out to 32, so that's good. This is why, by the way. And we, like you can see, the problem we have is we're only clearing out the first unit, and we want to clear out the entire buffer. Okay. So yeah, of course it is my own language, but it's still in development and very unstable. Sometimes I don't know what I'm doing. Oh, and that's another infinite loop. Isn't that delightful, my boy? Okay, let's look at this again. What's the matter with you, man? Let me think about this. Oh, I think I know. But that's problematic. I think I know, but I'm not entirely sure. Let me think about this for a second. We jump to main. Oh, we try. I think we're trying to... Are we trying to access forbidden memory? Are we? Huh. No, I don't think so. I don't think so, because it was infinite loop. And did I? Yeah, I did shut it down, so good on me. So if you don't understand what I'm saying, that's okay. Oh, I'm just documenting the funky process of coding in an experimental in development language, which is, you know, exciting in and of itself. And obviously, you know, utilizing the language to do things is, you know, the only way to develop it, because this is when I find the bugs, right? So anyhow, what's the problem here? I wonder, can I do it without the alias? That would be a good way. That would be a good way to expose how badly this works. Okay, all right. So let's try that again. Still infinite loop. What's the matter, man? I do not like this. Why are we on an infinite loop? There we go. Okay, so I'm going to explain that real quick. Okay, so yeah, I'm going to be honest with you people. I've been coding entirely on C for the last 2.5 months, and sometimes I forget when I transition between languages that first off, the operators are different. The operator precedents are different, and I have operators that are non-existent on other languages. So okay. The way this works, and this is a thing that happens a lot with the referencing, is that um the way that I call it caucus, cau- caucus, that's caucus, like Calcutta. So the way that works is it looks at a how do you say expression. It looks at an expression, right? Let's say 8 plus x plus 8 colon and some the reference. Let's say, right? It looks at some the reference. It looks at some expression and it goes like this. Okay, so it separates every time it encounters an operator, right? So plus is an operator, right? Colon here is an operator. This is the subscript, the left subscript and right subscript. That's also operators. So every time it encounters an operator, it says, okay, so that's a token. So it separates, right? And the problem it has is that it pushes every token with the operators it has to the left of it, okay? And it stacks them. It stacks them basically. So it would be the stack would look like this: x plus 8, the yeah, something like this, if I remember correctly. Ah, no. The subscript is a special case. It will separate it like that. And what it does is it evaluates from the, in this case it would be bottom up, but it's actually top. It's actually top down, so this would be top. So top, bottom. Okay, I'm actually going to call it bot. So it evaluates like that, and it does a couple funky things. No, actually, wait. I got confused. So I'm sorry. It evaluates from the bottom to the top. So actually, I was right the first time around. This is the top and this is the bottom. Okay, I'm sorry. I'm sorry, people. Okay, so it will evaluate from the top to bottom, and the state of the evaluation will change depending on the operators encountered, and some operators do basically nothing. Like no plus, it's just you know it's plus, right? You want me to explain addition? It's not that difficult, but so it recalls that to something you must add 8. And the way the precedence works is a little bit funky, right? If you have another operator, it just pushes that, and it figures out the precedence in strange, funky ways, which I really don't want to get into because I'll be here all day. But the point is that the colon operator is like it's like the when you use brackets, right? It's like when you use brackets, something like this. No, and what it does is it works like open bracket. Is that the parentheses? Parentheses. It doesn't matter. It's like you open one of these, and right at the end of the expression, it encounters another parentheses. Okay, so it's basically like a quick way to do that. And it closes right at the end of the expression or when you utilize another colon. And basically what that does is it says, so let me clean this up. It says solve all of this, then separately solve all of this, and then combine the results. So it's like a way to uh, do another kind of how do you say? It's like a way to work with precedence, to just be explicit about the precedence, right? Like what constitutes its expression. And when you realize a logical operator like the double ampersand, the logical and, it does the same thing. It separates and it says, okay, so solve this first, then solve this, then and both the results. It's something along those lines. So what happens here is that without the colon, it tries to add to the reference and then the reference, funky things like that. When you put it like this, it says, okay, so these are two separate operations. It's the reference first, then add, right? So, okay, sorry if that's a long rant, but I feel like I should explain some things. Okay, so all right, let's look at the console and see if the program did what it had to do, because that was sort of the point of all of this. And it did, kind of. It did, kind of. Because we do not have 32 bytes. This is 32 bytes. This, this is 64. I keep getting confused, man. We would have thought 16 by 4, 64, right? Professional programming and all of that. I'm tired, man. I'm really, really tired. So anyhow, that's 64. So alright. Um, let's try with the alias. And actually, let's try doing the dynamic aliasing and see if that works. Okay. So let's do this. Let's take it here and let's see if that works. Okay. Because I remember having implemented dynamic aliasing, it should work. So let's try it. Okay. Let's moment of truth. Ah, that's an infinite loop. That feels bad, man. It feels bad, man. Ah. Okay, so perhaps I implemented it and it's not all that good. I feel so bad. This was supposed to be a quick demonstration and it's turned out to be something entirely different. It does not matter. Okay, so let's just do it like that. And when we run it, we should see what let's okay, so alright. So now our buffer has been cleared. That's nice, and we have a 64. That's hexadecimal. That's what the 0x here means. So we have 64 in our counter. Okay. All right. And as you can see, that x24 there disappeared. So what I'm going to do is just for demonstration, and this time it's not going to take me that long, don't worry. Just going to say char and copy to counter, and I'm going to whoops, sorry. I'm going to increase counter, so get rid of that, and this will iterate. It should iterate about how many? 64 times total. Last time it was iterating 1, 2, 3, 4, 5, 6, 7, 8 times, and now it's going to go char by char. And so this second byte here should not be cleared. Alright, let's try that. And let's go. And it was cleared. What kind of sorcery is this? Oh, I know. Oh no, I don't know. Okay, why? Why was it cleared? That makes no sense. That's not supposed to happen, man. Why? Why did it do that? Hmm. If I delete this over here. Mm. And if you think it's fun seeing me fail, you have no idea how good it feels. You have no idea, my friend. So, let's see. Can't. Right, so let's just. I'm just going to ditch the aliasing. It's been very disappointing thus far. Let's just ditch that. Go into y. And let's try that again, shall we? And hopefully, this time, it will not clear out the second part. And it didn't. Okay, now it didn't. So apparently my aliasing is not as good as I thought it was. I've learned that lesson. It works. It kind of works, but not really, right? So that's just a thing that happens. I'll refine it with time. I just barely implemented it last week, I think. So it's weak. It's weak. I have no fear of admitting to that. So let's do Hello World, okay? Let's do Hello World, and now that I'm done messing around with loops and failing at it for the most part, let's actually try doing some actual, just a string copy, right? Like a outright string copy, and putting a null terminator in order to clear out the underside, the garbage in the buffer, right? So, like I touched on before, we don't really have a way to, and I'm just going to get rid of this because we don't need it, and the counter as well. So, like I was saying, we don't really null terminate strings, like not in the sense that you would do in C, right? In C, you need a null terminator in a string in order to know when to stop reading that string. But like I told you, in Peso we store the size of the string because, I don't know, we're crazy. We like to do crazy things. And so we do that kind of crazy thing, which is storing the size of the string. And so if I change the typing size to string, what I'm going to do is first I'm going to do, without any kind of clearing of the buffer, I'm just going to copy a straight up hello world, which is just a thing. I don't know why hello world, but it's the classical thing to put to the console, and so let's work with that. All right, and let's bring out the console, and this time I'm going to do it without the memory layout, and it gave us hello world, but we have all the garbage that's in our buffer, right? Because this might be what you get when you just grab an initialized buffer, maybe something you dynamically allocated. You would get this kind of mess, so you need a way to either clear this out or signal to the program that it needs to stop reading there, because it is the way my string copy works. It has no way of knowing if you want or do not want to copy to set the string to this value and nothing else than that. And so discard everything else, or you want to, let's say, insert a given string at a given position. And I prefer the behavior of just insert this many characters at this position and nothing else, unless, and you you should have been waiting for that, right? The unless I give you this, right? And this, if you don't know what this is, I'm sorry, man. I've been talking about null termination for a while. If you didn't know what this is, well, you didn't understand anything and probably clicked away a while ago. So I'm not worried about that. I'm not worried about you because you're not here. So we put the null term in there, and this is not an actual. This is, and that's the important thing. This is not an actual null that's inserted, though. For all intents and purposes, if there's enough space on the buffer, there will be a 0. But that 0 does not need to be there. Okay. So what this does in actuality is it just clears everything after the string you insert, right? Simple enough? Simple enough. So to better demonstrate that, let's try this. We will insert this null terminating string at a given position, and it should give us this as SDH whatever, and then this, okay? And everything after that should be zeroed out, right? It should be null. So let's try that. Let's bring out our little console here, and let's run it. And here we go. So let's see. I said X at position 4 and gave it here this white space thing. And so 1, not well, forgive me, 0, 1, 2, 3. Okay, so now 4, and here's where this begins. Tuk, 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 tuk. And no garbage, right? But here's the important thing. You do not need to store that null terminator because the length of the string is recorded. And so the Peso will know, internally. The C interpreter will not know this, unless you point it to the metadata block. It's a whole ordeal. You can do it, but I'm not gonna get into it. You do not need to store that null terminator. That's all I wanted to say. You do not need to store it. And I'm going to show the memory layout just for kicks. And as you can see, okay, let's see. Yep. And wait, what? 41. 41? That's not right. 41, are you sure, man? That's an A. Wait a minute. It did not clear it. What? Oh, I think I know. Or do I? Wait a minute. It was supposed to clear the damn thing. Why didn't it? Alright, so apparently apparently I do not know my own code. Why didn't it clean the damn thing? Well, that's another bug I need to look into. I just made the string copy yesterday. I said, yeah, string copy, not that difficult. I can implement string copy. Okay, alright, that's okay, man. That's okay. But I think that if I do it like this? Because I remember testing this and it did work. It worked when I tested. That's a typical excuse, right? That's a typical excuse. And it's like, it works on my end. Like, yeah, it doesn't work on mine, man. It does not work on my end. Such a common way out. Fuck's sake. Alright. Yeah, okay, so it did clean it, right? So you can see it ends at the 21, right? So apparently, giving it an offset, uh, just ruined me for some reason. I can't tell why. Um, I'm gonna have to look at the code and fix that, but weird bug, weird bug. So alright, but we have hello world. Here we go. After how many? Alright, so after an hour and almost 20 minutes, we have hello world. We have peso hello world. Isn't that nice? Type money, 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 money if you're feeling it. And if not, do not type money. Okay, so we've had a good bit of fun today. I've showcased some of the basics of this very primitive and quote unquote experimental, interpreted, someday to be compiled language. We've had a few laughs, a few sec faults, a few infinite loops, and it's been grand, everybody. So, alright, I'll keep making these. I will not stop making these, and if you like them, let me know. And if you don't like them, let me know as well. You might as well do that if you watched this far. So, thank you for watching. Have a good one. Bye.